Okay, everybody, we showed how to find the basis of a row space. Now we're going to show how to find the basis of a column space. Now, before I do that, I want to make one point. Say, I highlighted this in yellow. The row operations, they do change the column space of the matrix because when you move the rows around, the column vectors become different vectors. But even though they change the column vectors, they don't change the dependency relations between them. And that's really important. And we're going to use that fact. We're going to use that fact in this in finding the basis of a column space. Well, there's two ways to do it. One way is just to sort of chicken out and say, you know what, I'm going to take this matrix. This is the original matrix we had in the previous problem. I'm just going to transpose it, and then I'll do row operations. So here's my row operations. And now these three row vectors, I'm doing like air quotes, are really, if you flip it back the other way, it's the column vectors of the original matrix and PAL. So in other words, this is, so one way you can find the basis of a column space is just transpose the matrix, turn it into a, do row operations, find the basis of that new row space, flip it back, and voila. Now I'm going to show you method 2, which I personally find more interesting. I mean, I'm not saying which way you should do it in terms of practicality, but the concepts of method 2 I personally find a little more interesting. For method 2, what we're going to do is we're going to do all the row operations that we did before. And if you recall, now I want to look at this these three columns here. Let me just freeze this for a second. If you recall, back in, this is actually example 2, we wanted to find the basis of a row space. So we took this matrix and we put it into, we did the row operations and we put this into a row echelon form. And I got these 3 row vectors, okay? But now we're going to use this to find the column space of the same matrix, because we could see, once we have it in this form, we can see very clearly that column 1, column 2, and column 4 are independent of each other. Just for example, if I have column 1 and column 2, they're not multiples of each other, so they're clearly, they're independent of each other. But if I take all the different linear combinations of column 1 and column 2, I will never produce that 1 down there, because you see there's the, I have a 0 and a 0. If I would take the column and column, again, I'm looking at the column vectors here, not the row, I'm looking at the columns now. So I take column 1 and I take column 2 and I try to make combinations of that to get column 3. That ain't never going to happen, because I have a 0 and a 0, and I can take all the combinations I want. I'm never going to get a 1. So we see that these 3 vectors are linearly independent of each other. I'm just going to mark them out. So this column here, that column there, and that column there are clearly independent of each other. And whereas column 3, by the way, is not, because I could always subtract column 2 from column 3, and I turn that 1 into a 0, and I have like a -2 here or something. Then I could add 2 of the first column 1, onto column 3, and I get a full row of zeros. So column 3, which is a vector, a vector 3, column 3 can be written as a linear combination, so I can just boot that out. But these 3 guys are independent. Now, these 3 guys here are not, well, let me just let me finish that. I want to make an important point. What I do now is I take the corresponding vectors. So since I see column 1, 2, and 4 are independent in the original, in the new row reduced matrix, that means that column 1 and column 2 and column 4 must be independent in the original matrix. And that was the point I was making, that the dependencies don't change. Even though when I do these row operations, it changes the column vectors, but it doesn't change the dependency. That was the point I was making. So that's column 1, column 2, and that was column 4 of that original matrix. And they are linearly independent, and therefore we've now found a basis of the column space. And again, I'm making use of the fact that when I do these row operations, which is what I did in example 2, when I do the row operations, I was changing the column vectors, but not changing the dependency. Now, why don't I just, now when we did it the other way, we just said, okay, the three rows of the new matrix B, that's my basis. But here I'm not saying that. I'm not saying that this guy, that guy, and that guy are the basis, because they're not. They're totally different. They're totally different vectors. They're changed. But what I am saying is that since they are independent, the original columns 1, 2, and 4 must be independent. And it's a subtle difference, but an important difference. And this is a method for finding the basis of a column space. Well, you may have noticed, or you may not have noticed, that when I looked at this same matrix here, we started with this big matrix here. So this matrix here, when I found the basis of the row space, we had 3 vectors in it, three row vectors. Now, again, these are vectors from R4. But then when we found the basis of the column space, we also had 3, I lost it already. We also wound up with 3 vectors. Now, coincidence or not? So turns out it's not a coincidence. And this is extraordinarily important, that theorem 4.15, that the row space and the column space have this equal dimensions. So if matrix A is an M by N matrix, does not have to be a square matrix. It could just be any matrix. The row space and the column space are going to have the same dimension, which is amazing because they're different types of vectors. Because one could be, the row space could be, the row space could be R4 vectors, and the column space could be R5 vectors. They're totally different types of vectors. Yet when you figure out the dimensions, they're going to wind up being the same. The equal size subspaces of the original thing. So, like an example we had before, these vectors were part of the vector space R4, and they formed the subspace of R4. The other ones made a subspace of R5, which is a whole different type of vector. Yet the subspaces had dimension 3. That's what we're saying. The column space and the row space have the same dimension. Now I'm going to walk you through the proof. It's like about 1 billion steps, but it's none of it is beyond our comprehension. Just a lot of algebra. But then again, this class is an algebra class. So we're going to look at a matrix A, and we're going to let V1 through Vm be the row vectors. So that's the horizontal guys, and U1, U2, UN are going to be the vertical, column vectors. Now, let's say the row space of A has dimension R. I'm just making up a variable R. So R is the dimension of the row space of A. And let's say it has a basis, B1, B2, up to BR. And where each BI is BI1, BI2, BIN, da da da. So we're going to use this basis, and we're going to write the row vectors of A in terms of that basis. So vector 1, which is that first horizontal vector, is C11 B1, C12 B2, da da da. It's a linear combination of the vectors from the basis. And vector 2, which is the second row, is a linear combination of the other vectors, and all the way dot 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 down the line. By the way, one big thing in linear algebra, there's a lot of dot dot dots. So we're going to rewrite this system of vectors as follows. The first row, A11, A12, A1n, dot dot dot, that's going to be C11 times the B. This is basically B1, and that's C12 times B2. All I'm doing here is this down here is the same as what I have here. I'm just writing out what B1 is. B1 is all those guys right there, and B2 is all them guys right there. and so on and so forth down the line, and until you get down to the bottom one. So I'm rewriting it, and now I'm only going to take the entries corresponding to the first column of matrix A, and I'm going to get a system of equations as follows. I'm going to get that A11 is C11 B11 plus C12 B21 plus da 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 plus C1R B1R all the way down the line. And if I look at the entries for the jth column, I'm going to get A1J is C11 B1J plus C12 B2J plus C1R BRJ da 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 down the line. And now I'm going to let the define these vectors C, both C. So the Cith vector is going to be, this is actually a vertical vector. That's why I have the little t means it's vertical, because I'm transposing it. But it's C1I, C2I, dot 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 up to CMI. And now the system for the jth column, I can rewrite it now in vector form, and it's going to look like this, similar to what we did before. So A11, A21, da 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 to AM1, that's B11, C1 plus B21, C2 plus da 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 da, all down the line. Now, let's analyze what we got here. Each column vector of A is a linear combination of R different vectors. And we know that the dimension of the column space of A has to be less than or equal to R, because, which is the dimension of the row space of A. So the dimension of the column space is going to be less than or equal to the dimension of the row space. And if we do this in reverse, do the whole process in reverse, we're going to find that the dimension of the row space is going to be less than or equal to the dimension of the column space. Well, if Bob is less than or equal to Bill, and Bill is less than or equal to Bob, so Bob and Bill must be the same. Don't ask me where I got Bob and Bill from, but that shows that the dimensions. Now, again, this is a little hairy, a lot of substituting and rewriting, but it's not that none of this is beyond our ability to comprehend. The result now is spectacular, because now that we know that row spaces and column spaces have the same dimensions, so we can now make a new definition. We can define something called the rank of a matrix. And the rank of a matrix is the dimension of the row space and or column space, because they're the same thing, of a matrix. And we call that the rank. And in a certain kind of way, this reminds me, it's analogous in a certain way. When we couldn't define we were not able to define the dimension of a matrix until we saw that every basis had the same number of vectors. Well, now I couldn't define the rank of a matrix until we saw that row spaces and column spaces had the same dimension. So that's really what it is. The dimension of the row space and the dimension of the column space, which is the same thing, is called the rank of a matrix. So I know what you're all thinking. Gee, this is wonderful. How am I going to find that? How do I find this? So here's what we do. We take a matrix. Here's our matrix here. We put the matrix into row echelon form. We see that there are 3 non-zero rows, which means that the dimension of the row space is 3. Well, that's the answer then. Then the rank of A is 3. Now, I didn't even bother trying to find the dimension of the column space. Doesn't even matter, because once I know the dimension of the row space is 3, then that's my answer. The rank is 3, because like I said, the row space and the column space is the same. It's equal to the rank, and it's all good. And that concludes this video. We're not done with the section. There's still plenty more, but that's it for now. Till the next one.